Hello and welcome to this video. We're going to talk today about errors, which are things which affect the quality of our data. Now, before we go on to that, it's really important that you have an understanding of accuracy and precision. This is something that we've already learned in my lessons. However, if this is something that you're not familiar with, please do feel free to have a look at the slide there, press pause, and make sure you're kind of clear with those ideas of accuracy and precision, because they are words which often get misused in science. Assuming you're okay with those ideas, let's get cracking with errors. Now, errors in general are things which affect the quality of our experiments. If you have high errors, then it means that your results may not be accurate and they may not be precise. And in physics, we have two types of errors. We're going to talk about those today and try and relate them to our experiments. The first type of error is what we would call a systematic error. Now, as the name suggests, systematic errors are to do with the system. And what they do is they affect our data in the same way. So we might be taking multiple readings, and we notice that all of our readings have been affected in the same way. So in other words, they might be too big or too small, but they are too big or too small by the same amount. All right, now on the graph, you can see on the screen is an example of systematic error. The blue line is what we measure in an experiment, and the black line is what we should measure in the experiment. Now, what you notice is that the blue line is consistently above the black line, and therefore every reading is too big by the same amount. And in this case, every reading is too big by the same amount, which is 1. 1 is the y-intercept in our graph. So sometimes we can tell a systematic error purely from the existence of a non-zero y-intercept. So we're expecting a relationship to go straight through the origin, and what we find is actually that it doesn't. And that might be to do with a systematic error. Okay, now when this happens, this is specifically called a zero error, and it's usually a problem with the equipment that we're using. And we'll give an example of that in a second. But it's quite easily resolved. If we know that y-intercepts, for example, in this case 1, all we have to do is subtract 1 from all the readings, and we get back to the number we should have in our experimental values. Okay, so systematic error, although it's kind of annoying, it's fairly easy to get rid of. Let's give an example. This is a set of scales which has not been zeroed. Okay, and if we were to use this, if we were being a bit careless and didn't press the 0 button, then all of our numbers would be too big by 482. Obviously, if I have 0 things on there, then it shouldn't be reading anything. It should be reading 0. However, in this case, we need to press the 0 button or the tear button to make sure that we get rid of that 482 before we start. And sometimes we forget to do that. Okay, every piece of data would be too big by the number 482, and that would be a systematic error. All right. The next type of error is called a random error. And again, clue really is in the name. A random error will affect the data in different ways. Okay, some of our data points might be too big, some of them might be too small, and they might be too big or too small by different amounts. Okay, so this is probably one which is a bit harder to deal with, because we never know what random things are going to be. Random is random, and therefore it, in theory, is difficult to process. Now, when we're plotting a graph, we can see random error by the spread of points around the line of best fit. So we've drawn a line of best fit, nice, goes to the origin, no systematic error in this case. However, we notice that some of the points are above and some of the points are below that line. It's called deviation. And it's shown, that shows the existence of random error. Now, the greater that deviation, the greater that spread, the greater the amount of random error. So if the points are really far away from the line, there's a lot of random error. And if they're really close, there's a little bit of random error there. All right. Now, an example of random error would be reaction time. Now, this is quite a confusing one for students because they often think it's a systematic one. Actually, reaction time is not always the same. Your reactions change, and therefore they are a little bit random. You might be able to roughly give an average value. However, you don't always know your reaction time. So if you're measuring something using a stopwatch, there's always reaction time, which is a random error, and that's why time values may end up being a little bit wobbly and having a little bit of deviation around that central line. It's not always the same. And the way we can get rid of random errors is nice and easy. What we do is we average things. If you think about this, using the example of time, I might measure the time once, which is too big, and I measure the second time, which is too small. Well, if I calculate an average, I'm therefore adding a big number to a small number, which should average out to make the, inverted commas, correct number. It doesn't mean that we remove the error entirely. However, it doesn't allow us to compensate for that error. Okay, so this is why we take average values whenever we're doing experiments, because it will eliminate or help compensate for random errors. So there you go. We've got two types of errors. That's random and systematic. And your job is to think about experiments that we've been doing and try and designate whether those errors or any issues with the experiments are systematic or